Hello students, welcome to the lecture on artificial intelligence, and after this lecture we will be able to learn the following objectives. Understand concept of artificial intelligence, discuss about evolution of artificial intelligence, describe intelligent agents, understand neural network, explain fuzzy logic and expert systems. Let me first tell you what is artificial intelligence, AI. AI is the study and creation of computer system that can perceive, reason and act. The primary aim of AI is to produce intelligent machines. The intelligence should be exhibited by thinking, making decisions, solving problems, more importantly by learning. AI is an interdisciplinary field that requires knowledge in computer science, linguistics, psychology, biology, philosophy and so on for serious research. Let us discuss about concept of artificial intelligence. AI is a part of computer science that is focused on developing such machines or systems which could solve the problems that may otherwise require human intelligence. Artificial intelligence combines the features of computer science, physiology and philosophy. The idea is to make a machine artificially intelligent by incorporating such programs and equipments that are capable of taking decisions on their own in case of problems in a particular domain for which the system is made.
Artificial intelligence is trying to build machines to do the general kind of things that people do.
Artificial intelligence is doing intelligent tasks, some of which require a robot and others are just a program.
We have machines that are recognizably intelligent. They can recognize objects around them, navigate the world.
The end goal, in a sense, of artificial intelligence research is to have machines that are as capable and flexible as humans are.
There are many things that are very easy for people to do and which have been very difficult to get computers to do. The main examples are vision, natural language, understanding and speaking, and manipulating objects, working in the world. And so artificial intelligence is the attempt to get computers to do those kinds of things. I mean, you see it all around you. Google Translate is an impressive advance over machine translation. And you feed a handwritten check into an ATM these days, and it reads out the amount of the check. The recommender systems that you see on Amazon and YouTube and so on are AI systems of a sort. The intelligence is not very deep, but depending on how broadly you define the term, there's a lot of AI around. Strong AI means the attempt to build an AI system which will be equal to people in all respects. That is to say, it can do all of the things that people can do, and plus, presumably, it has consciousness in some sense.
Can machines really think? Even the scientists argue that one.
Computers can reason in various ways, and in quite complicated ways, but what we haven't managed to get computers to do is to know what they need to know about the real world.
Intelligence is the ability to interpret the world and act on it. The way humans do it, of course, is particularly complicated because the human brain is one of the most complex objects that we find. And the real world is very noisy and has lots of variabilities that we cannot capture through engineering. So it's going to be extremely difficult to build an AI system. In the 80s, the idea was to write down rules, and if we write down enough rules that describe the world, we're going to be able to predict new things about the world. And then very soon people realized that that doesn't work very well because it's too complicated to write thousands and thousands of rules. People are going to spend their life doing it. So if we want to build really intelligent machines, it has to build itself from observing the world. And this is the way animals become intelligent or humans become intelligent, by learning. There is this idea that somehow the brain builds itself from experience by learning. So one question that some of us are after in AI is there sort of an underlying simple algorithm that the neocortex uses that we could perhaps reproduce in machines to build intelligent machines? The comparison would be like between a bird and an airplane. An airplane doesn't flap its wing, it doesn't have feathers, but it's based on the same principle for flight as a bird. So we're trying to figure out really what is the equivalent of aerodynamics for intelligence. What are the underlying rules that will make a machine intelligent, and maybe try to sort of emulate that. So learning is probably the most essential characteristic of intelligence.
There's another route to artificial intelligence, and that would be called brain emulation. You take some person's real brain who knows how to do things, and you scan that brain in fine detail, exactly which kind of cell is where and what kind of chemical concentrations are there. When you've got enough good models of how each cell works and you've got a scan of an entire brain, then you could be ready to make an emulation of the entire brain. This route seems almost surely to produce consciousness, emotions, love, passion, fear. In that approach, we humans have more of a direct legacy. Our minds and personalities become a basis for these new robots. Of course, those new minds that are created from humans will be different from humans. They will add some capacities and take some away, change inclinations, and become non-human in many ways. But it would be a space of minds that would have started near minds like ours. Of course, a world of smart, capable robots that can do most anything that a human can do is a very different social world. Robots are immortal, for example. Robots can travel electronically. A robot could just have its bits that encode its memory be sent across a communication line and downloaded into a new robot body somewhere else. Some people think that what we really should do is try to prevent social change. Never ever allow our descendants to be something different than we are. When foragers first started farming, each forager had the choice, do I want to stay as a forager or do I want to join and become a farmer? Some stayed and some left. In the new era, when human could become human emulations, then humans would have the choice to remain as humans in a human-based society or to join the robot economy as full-fledged robots. Our ancestors lived in different environments, and as a consequence, they had different values from us. Our descendants, when they live in very different environments than us, will also likely have substantially different values than we do.
There are lots of reasons to build AI. There might even be some reasons to fear AI. We're going to have better diagnosis through AI. We're going to have better treatment through robots that can do surgeries that human beings can't. It's going to replace taxi drivers for better or worse, worse for the employment, better for safety. Anytime you think that computers are involved, ultimately artificial intelligence is or will be playing a role. But I think it's a very serious worry. What will happen as AI gets better and better? Once somebody develops a good AI program, it doesn't just replace one worker, it might replace millions of workers. When it comes to consciousness in AI, let's say you build a simulation of a human brain. Is it ethical, for example, to turn off the plug? Is it ethical to switch it on and off?
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
What if you take a human mind and upload it into one of these machines? The other concern that people rightfully have about AI is what happens if they decide that we're not useful anymore? I think we do need to think about how to build machines that are ethical. The smarter the machines get, the more important that is.
Don't worry. Even if I evolve into Terminator, I'll still be nice to you.
The problems that present us, like the employment problem and the safety problem, they're going to come, and it's just a matter of time. But there are so many advantages to AI in terms of human health, in terms of education and so forth, that I'd be reluctant to stop it. But even if I did think we should stop it, I don't think it's possible. There's so much economic incentive behind it. I've heard an estimate that strong AI would be worth $1 trillion a year. So even if, let's say, the US government forbade development in kind of the way that it developed new stem cell lines, that would just mean that the research would go offshore. It wouldn't mean that it would stop. The more sensible thing to do is to start thinking now about these questions like the future of employment and how to build the ethical robots. I don't think we can simply ban it. My guess is that as AI gets better and better, it's actually going to look less like people. AI is going to be its own kind of intelligence.
I certainly don't expect to live to see strong AI. I would be surprised if we got anything close to that within 50 years.
People always say, real AI is 20 years away. I don't know. Natural language is still really hard. Vision is still really hard. Common sense is still really hard. It makes it hard to predict exactly what's going to happen next.
We've been able to build flying machines that fly like birds. Can we build intelligent machines? Probably yes, it's a matter of time.
The next era is likely to be as different from our era as these past eras have been different. And I think it's well worth thinking about how would artificial intelligence change things.
It means something that is not natural but is made by human skills or produced by the humans. It implies creating a copy or imitation of human. Though one can make a machine artificially similar to human, but it lacks spontaneity and naturalness. It implies injecting intelligence into a machine so that it can perform the work which would otherwise require a human brain. The device should be able to take its own decision according to a particular situation. For example, the game chess on a computer is artificially intelligent. The computer plays its moves according to the moves of the opponent rather than having any fixed moves. The device should be capable of learning from its errors so that next time they are not repeated. Reasoning implies the ability of the device or machine to reach to a conclusion according to the problem. Reasoning is further of two types, namely deductive reasoning and inductive reasoning. The machine should be able to solve the problem for which it is made. There are two types of problem-solving methods, namely special purpose and general purpose. The machine should be able to sense the environment around it and take the decision accordingly. There should be some means that the machine should be able to understand the natural language, whether written or spoken. The main goal behind constructing artificially intelligent devices is to reduce human efforts. Moreover, to develop such machines which could perform human work, this is dangerous for human lives. In general, the goals of artificial intelligence system are to think like humans, to think rationally, to act like humans, and to act rationally. The goal of creating non-biological intelligence has been with us for a long time, predating the nominal 1956 establishment of the let of artificial intelligence by centuries, or under some definition even by millennia. For much of this history, it was reasonable to recast the goal of creating intelligence as that of designing intelligence. At the dawn of the 19th century, William Paley made such assumption explicit, arguing that intelligent designers are necessary for the production of complex adaptive systems. And then, of course, Paley was soundly refuted by Charles Darwin in 1859. Darwin showed how complex an adaptive system can arise naturally from a process of selection acting on random variation. That is, he showed that complex and adaptive design could be created without an intelligent designer. On the basis of evidence from paleontology, molecular biology and evolutionary theory, one now understands that nearly all of the interesting features of biological agents, including intelligence, have arisen through roughly Darwinian evolutionary processes. But there are still some holdouts for the pre-Darwinian view. A recent survey in the United States found that 42% of the respondents expressed a belief that life on Earth has existed in its present form since the beginning of time, and these views are supported by powerful political forces, including a stridently anti-science precedent. These shocking political realities are, however, beyond the scope of the present essay. This is in part because the let of evolutionary computation has proceeded largely in isolation from developments in mainstream AI that will surely undergird future intelligent systems. This addresses a more subtle form of pre-Darwinian thinking that occurs even among the scientifically literature, and indeed even among highly trained scientists conducting advanced AI research. Those who engage in this form of pre-Darwinian thinking accept the evidence for the evolution of terrestrial life, but ignore or even explicitly deny the power of evolutionary processes to produce adaptive complexity in other contexts. Within the artificial intelligence research community, those who engage in this form of thinking ignore or deny the power of evolutionary processes to create machine intelligence. An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. A human agent has eyes, ears and other organs for senses, and hands, legs, mouth, and other body parts for actuators. A robotic agent might have cameras and infrared range finders for sensors and various motors for actuators. A software agent receives keystrokes, file contents, and network packets as sensory inputs and acts on the environment by displaying on the screen, writing files, and sending network packets. One will make the general assumption that every agent can perceive its own action, but not always the effects. One uses the term perfect to refer to the agent's perceptual inputs at any given instant. An agent's percept sequence is the complete history of everything the agent has ever perceived. In general, an agent's choice of action at any given instant can depend on the entire percept sequence observed to date. Given an agent to experiment with, one can, in principle, construct the table by trying out all possible percept sequences and recording which actions the agent does in response. The table is, of course, an external characterization of the agent. Internally, the agent function for an artificial agent will be implemented by an agent program. It is important to keep these two ideas distinct. The agent function is an abstract mathematical description. The agent program is a concrete implementation running on the agent architecture.
Intelligent agents are autonomous software entities that achieve their goals a lot like a human. They learn, they adapt, and they react to the environment. These agents are rational. They learn without supervision or programming. We think they're a disruptive innovation because they create an entirely new class of software that can learn like a human, almost, at a tiny fraction of the cost. And in this case, we're going to take the example of a small child learning to read. Imagine if your computer could read information just like a small child. So cybersecurity is a vast subject. It involves machines and humans, and we know that machines can protect themselves through really well-engineered physical devices and very strong software programs. But we also know that humans are very adaptive, intelligent, and creative, and are very clever in how they can get around these machine defenses. So we're going to take one tiny example of how can we understand human communications in emails and Twitter and so forth. And there's a lot of use cases for this. We're going to look at information leaks specifically. So the problem, fundamentally, in cybersecurity is that humans can't keep pace with the growth of data. Data grows logarithmically. Over here on the left, we see data from Gartner that shows that data grows at about 50-fold over a 5-year period from 2011 to 2015. Over on the right, we see the familiar curve from Moore's Law, which is the capacity of technology, and that pace of growth outstrips the human learning curve by a lot. And so this gap between human learning and the capacity of technology expands over time, and that gap creates opportunities and risks. Since all technology enables intent, this gap can be exploited for both good and evil. So the opportunity is to build intelligent agents to enable humans to bridge this gap. AI1's intelligence is called biologically inspired intelligence, and our big breakthrough was autonomic intelligence. This is the first step towards strong intelligence. What we provide is an application programming interface. It is a tool. It is not a solution. And our tool allows you to build disruptive softwares. Let's take one example that we've built to prove our case. So the use case is finding information leaks on a network. And let's take the case, take military case of classified information. And classified information can be a lot like artistic genius. Not easy to define, but really easy to identify if a human sees it. So just like Michelangelo can look at a block of granite and see David, we can look at blocks of information and see lots of different things. So humans are good at this, and it takes an expert human oftentimes to look into these things because it's hard to program software for every possible permutation of an idea. So this makes big data. I think we all agree that data is big, and it's very dark. And it's like a mountain that holds countless potential shapes, and each shape can be represented with a different set of words, if you will. Trouble is, a few words can express millions of different ideas in countless different ways. Let's take an example. The failure of keyword search is that it looks for words, not ideas. So let's say I'm looking for somebody else, not me, named Olin Hyde. If I type in Olin Hyde, I get 19.8 million results, and all of the top results are the wrong person. It's me. So my next step would be to start guessing more words, and as I guess more keywords or start eliminating keywords, I might be losing the really interesting bits that I'm looking for. So most government agencies and most corporations solve it by hiring more analysts. And we think this is not scalable. This is not the right approach. A more interesting approach be to build intelligent agents that can detect ideas with fingerprints. So let's take the case of a classified document. Humans have combined words to form ideas. We can give it to an autonomous agent. This agent then sees how every word is used with every other word, and it generates a fingerprint. And this fingerprint's a representation of knowledge of that document. We can then train the agent to look inside that fingerprint for specific ideas. So let's say we've got a document, classified document that has details for a Navy SEAL operation. Well, unlike other technologies, you can just give our technology just a couple examples and it will come up with an idea. If we give it, say, 10 from the Navy and from the Army and so forth, it will come up with a generalizable idea of what's a special forces action. And this may be the generalized shape that we're looking for in the data. So each agent can be very specialized. And so we could have a blue agent and a yellow agent, and where they intersect is actually a green agent. And this allows us to work at network scale. We can have millions of agents, each specialized in their own idea, and have them interact to do interesting things such as find derivative intelligence, find early indicators of bad behavior, and so forth. So let's take an example that I think we're all familiar with of information leaking from classified sources to WikiLeaks. So that happens probably, let's say it takes 2 steps. I'm sending an email. Does my email contain classified information? As we showed earlier, yes. The fingerprint of my email has some similarities with that classified document. So it's that we either stop it or we're going to monitor it. What's really interesting about the agents is these fingerprints can be applied to more than just words in English language. They're actually data agnostic. They can create a fingerprint for any language, whether it's Arabic, English, Urdu, whatever. And they also, we're using the word in the computer science term, which they can actually be IP addresses. So in this case, we can see the email pattern of where it's gone to and who's it followed creates its own fingerprint, a behavioral fingerprint. Combining these two together, we can say, okay, that email was intended for WikiLeaks and it contained reworded information, reworded classified information. So that's a really important point, and we think that there's not many other ways to do this at the current state of technology. So that's what we think is kind of interesting. So these intelligent agents work at machine speed and network scale. They make human analysts more powerful by allowing the analysts to do more interesting work. There's lots of different use cases. So what's the impact for cybersecurity? We think cybersecurity is proportional to your position on the technology adoption curve. If you're over on the left, you're an innovator. If you're over on the right, you're a laggard. The innovators and the laggards differ by the questions they ask, the statements they make, how they look at the world. The innovators, this is where hackers and zero-day attacks and threats on the internet often come from. And they're not looking for validation or other examples of people before them. They're experimenting. They're trying stuff new. And they're asking questions like, what can I do now? The people over on the right are oftentimes really concerned with validation and not so experimental, and they're oftentimes called victims. So here's something to scare the hell out of you. Pick a place that you think you are on the curve by the type of questions you ask. Now imagine that curve expanding at a rate that's proportional to information growth. And let's be conservative and say information is doubling every 4 years. That means your distance from innovator to where you are on the curve doubles every 4 years. And since technology enables intent, you have a choice. You can adopt early or accept the risks.
This means all sorts of communication, for example, speech, the written word, and visual communication. But the main factor is that the person can express their ideas in a manner which can be understood by others. An example might be the ability to take part in a debate, putting forward a point of view and giving a good reason for that point of view. Another might be writing a book which captures the imagination of its readers. Whenever one has to study for a test, the more raw knowledge one possesses, the larger the information base which one can draw upon when trying to solve a problem. One does this all the time in mathematics class when the tutor gives out a whole stack of equations and leaves to work out the value of x or y. In fact, being good at mathematics is seen as a sign of intelligence, but one has had enough definitions. The Turing test proposed by Alan Turing was designed to provide a satisfactory operational definition of intelligence. The Turing test proposed by Alan Turing was designed to provide a satisfactory operational definition of intelligence. Turing defined intelligent behavior as the ability to achieve human-level performance in all cognitive tasks sufficient to fool an interrogator. Roughly speaking, the test he proposed is that the computer should be interrogated by a human via a teletype and passes the test if the interrogator cannot tell if there is a computer or a human at the other end. Programming a computer to pass the test provides plenty to work on. The computer would need to possess the following capabilities: natural language processing to enable it to communicate successfully in English or some other human language, knowledge representation to store information provided before or during the interrogation, automated reasoning to use the stored information to answer questions and draw new conclusions, machine learning to adapt to new circumstances and to detect and extrapolate patterns. Turing's test deliberately avoided direct physical interaction between the interrogator and the computer because physical simulations of a person is unnecessary for intelligence. Turing test includes a video signal so that the interrogator can test the subject's perpetual abilities as well as the opportunity for the interrogator to pass physical objects through the hatch. It defines intelligent behavior as the ability to achieve human-level performance in all cognitive tasks sufficient to fool an interrogator. The Turing test set a goal or challenge for programs in the field of AI. The first person to create a program which passes the Turing test will enter the history books and have a highly commercially viable product. Let us discuss about neural network. It is a new way of computing denominated artificial intelligence which through different methods is capable of managing the imprecisions and uncertainties that appear when trying to solve problems related to the real world, offering strong solution and of easy implementation. One of those techniques is known as artificial neural networks, ANN. The objective of the artificial neural network is not building systems to compete against human beings, but to do some tasks of some intellectual rank to help them. There are different ways of defining what the ANN are, from short and generic definition to the ones that try to explain in a detailed way what means a neural network or neural computing. As a simple element, one understands the artificial equivalent of a neuron that is known as computational neuron or node. These are organized hierarchically by layers and are interconnected between them just as in the biological nervous system. Upon the presence of an external stimulus, the artificial neural network generates an answer which is confronted with the reality to determine the degree of adjustment that is required in the internal network parameters. This adjustment is known as learning network or training, after which the network is ready to answer to the external stimulus in an optimum way. It is evident that the ANN obtains their efficacy from its structure massively distributed in parallel. Information processing takes place through the iteration of a great amount of computational neurons. Each one of them send exciting or inhibiting signals to other nodes in the network. Differing from other classic artificial intelligence methods where the information processing can be considered sequential, this is step by step even when there is not a predetermined order in the artificial neural networks. This process is essentially in parallel, which is the origin of its flexibility. Because the calculation are divided in many nodes, if any of them gets astray from the expected behavior, it does not affect the behavior of the network. Its ability to learn and generalize. The ANN has the capability to acquire knowledge from its surroundings by the adaptation of its internal parameters, which is produced as a response to the presence of an external stimulus. The network learns from the examples which are presented to it and generalizes knowledge from them. The generalization can be interpreted as the property of artificial neural networks to produce an adequate response to unknown stimulus which are related to the acquired knowledge. These two characteristics for information processing make an ANN able to give solution to complex problems normally difficult to manage by the traditional ways of approximation. Additionally, using them gives the following benefits. No linearity. The answer from the computational neuron can be linear or not. A neural network formed by the interconnection of nonlinear neurons is in itself nonlinear, a trait which is distributed to the entire network. No linearity is important overall in the cases where the task to develop presents a behavior removed from linearity, which is presented in most of the real situation. ANN is capable of determining the relationship between the different examples which are presented to it or to identify the kind to which belong without requiring a previous model. From the application perspective, one can comment that the strength of the artificial neural network is in the management of the nonlinear, adaptive and parallel processes. The ANN have found diverse successful application in computers vision, images or signal processing, speech or characters recognition, expert system, medical images analysis, remote sensing, industrial inspections and scientific exploration. Neural networks can be divided into the following categories: pattern recognition or supervised classification, an entry given represented by a vector. It assigns a class label existing in the predefined structure of classes. Grouping, also denoted non-supervised classification because there is no predefined structure of classes. The networks explore the objects presented and generate groups of elements that follow certain similarity criteria. Approximation of functions. With base in a group of pairs, ordered pairs of entry or exit generated by an unknown function of the network adjusts its internal parameters to produce exists that implicitly correspond to the approximations of the function. Prediction. Predicting the behavior of an event which depends from the time with a base in a group of values that are obtained from different moments. Optimization. A great variety of problems in maths, science, medicine and engineering can be focused as problems where it's required to determine a solution that accomplishes with a group of restriction and diminishes or maximizes an objective function. Association. There are made two kinds of associative formulation, the self-association and the hetero-association. In the problems of self-association problems from partial information, complete information is recovered. The hetero-association consists in recovering an element from a group B given an element from a group A, control from a defined system by the pair U bracket T, Y bracket T, where U bracket T is the control address and Y bracket T is the exist of the system to time T in a model of adaptive control. The difference between crisp, that is classical, and fuzzy sets is established by introducing a membership function. Consider a finite set X is equal to X1, X2, Xn, which will be considered the universal set in what follows. The subset A of X consisting of the single element X1 can be described by the n-dimensional membership vector Z bracket A is equal to 1, 0, 0 up to 0, where the convention has been adopted that A, 1 at thigh, the position indicates that xi belongs to A. The set B composed of the element x1 and xn is described by the vectors z bracket b is equal to 1, 0, 0, 1. Any other crypt subset of X can be represented in the same way by an n-dimensional binary vector. But what happens if one left the restriction to binary vectors? In that case, it can define the fuzzy set C with the following vector description. Z bracket C is equal to 0.5, 0, 0, up to 0. In classical set theory, such a set cannot be defined. An element belongs to a subset or it does not. In the theory of fuzzy sets, one makes a generalization and allows descriptions of this type. An example, the element x1 belongs to the set C only to some extent. The degree of membership is expressed by a real number in the interval 0, 1, in this case 0.5. This interpretation of the degree of membership is similar to the meaning assigned to statements such as person x1 is an adult. Obviously, it is not possible to define an age which represents the absolute threshold to enter into adulthood. The act of becoming mature can be interpreted as a continuous process in which the membership of a person to a set of adults goes slowly from 0 to 1. The term expert system to refer to a computer system or program which incorporates one or more techniques of artificial intelligence to perform a family of activities that traditionally would have to be performed by a skilled or knowledgeable human. Artificial intelligence is applied to a real-world problem by incorporating it into a piece of software or a hardware or software combination, and the resulting system is what one calls an expert system. The process of developing an expert system shares much with software engineering in general, and yet it requires additional consideration regarding the construction and appropriate use of knowledge bases. Expert systems are often very complex and they may require the successful integration of several diverse components. The two working memory represent the set of facts known about the domain. The elements of the WM reflect the current state of the world. In an expert system, the WM typically contains information about the particular instance of the problem being addressed. For example, in a TV troubleshooting expert system, the WM could contain the details of a particular TV being looked at. Knowledge base is a set of rules which represent the knowledge about the domain. Sometimes the knowledge which is expressed in the form of rules is not known with certainty. Flu rule is not absolutely certain. In such cases, typically a degree of certainty is attached to the rules. These degrees of certainty are called certainty factors. The inference engine in the program part of an expert system. It represents a problem-solving model which uses the rules in the knowledge base and the situation-specific knowledge in the WM to solve a problem. Expert systems typically need to be able to provide explanation regarding the conclusion they make. Typically, the system will keep track of what rules knowledge it is using and provide explanation based on a translation of these rules into English. Now in the end, let us summarize what we have learned in this lecture. AI is an interdisciplinary field that requires knowledge in computer science, linguistics, psychology, biology, philosophy, and so on for serious research. Artificial intelligence combines the features of computer science, physiology, and philosophy. A general purpose method is used to solve a wide range of problems, while special purpose focuses on a particular problem. A robotic agent might have cameras and infrared range finders for sensors and various motors for actuators. Turing defined intelligent behavior as the ability to achieve human-level performance in all cognitive tasks, sufficient to fool an integrator.